Hello everyone. In this video I'm gonna talk about metaprogramming in C++. What's wrong? So nothing. So the talk is over. If you have any question, I will be happy to answer. Okay, that joke was presented to me in our Discord channel for the Italian C++ community, but I think there is a lot to say about what's wrong in C++ metaprogramming. So just a couple of minutes on about who am I. My name is Andrea Griffini, and I've been professional programming for more than 40 years now. I started quite young in the early 80s, and I've been programming in many different fields. From started with actually off-the-shelf software for drawing and office support. Then I went to business software, then medical imaging, then I wrote, for a little period I was working on game engines on real time when I was in the United States. Then in the last 26 years I've been in a company that builds industrial robots, and mostly working on artificial vision and optimization problems. I started using C++ more than 30 years ago, before it was even a standard. And I'm old. Why I'm saying that I'm old? Because I tend to have this kind of negative view about new things that is very common in other people. I try to compensate for this bias, but just consider this when you're watching this presentation. So, what is metaprogramming? Is the first question that I wanted to ask. I want to put a definition. This is my definition, but it's not very far from what you can find on, say, Wikipedia. And in my view, is code that manipulates code. What does it mean, manipulating? To me, it means that a metaprogramming function is just a regular function, so it's code. It's a programming language where you can write statements and conditional and stuff. But the input or the output is at least partially composed of code. And code, as we know that programs manipulate data, they have input and output and computation, but to manipulate code, it means that you must represent code as data and to do your manipulation. And your output, that is data, has to be interpreted as code. And this is one of the way, in my opinion, in which the mantra code is data, that is code can be interpreted. There are many other ways, but this is one way to see this phrase. So, a few examples of metacode. The first is the simplest one. That means we want to write code that generates code. Input may be a number, and the output can be, a code definition of a static table containing data about that number. For example, I get 256 as input, and I want a table of 256 entries for the sine or cosine values to pre-compute those values. This is just one example. And another case is the opposite, where we have an input that is code and we want to analyze it. And maybe the output is not code at all. For example, we want to introspect in the fields and find something, compute something about those fields. I want to get the list of function called by a specific function or something like that. So input, in this case, code is input and the output is something else. And in the general case, we have code modification. So we get code as input and we return code as output, maybe after a transformation. We did something, we added something, we removed something in the process. One special case, very special case of code generation that is very common, very useful, is when we need to just produce code that is filling in of a template. So we received code as input, the template, we basically received the template and we do the substitution. Why I think this is not code analysis or not code modification is because the template is not really analyzed. It's just substitution. So it's treated as an opaque from a code reasoning point of view. It's just an opaque piece of data. So we just fill in the form. This is normally called in the metaprogramming jargon quasi-quoting. That means it's not really just a static piece of code. It's not quoted code. It's not between double quotes, but almost. It's the static piece of code with some substitution. You know, here and there are markers and that are replaced with parameters or expressions more in general. And this is called quasi-quoting. So those are all three metacode example. And to manipulate the code and generate the code, we need a way to represent the code, as I said before. And the simplest form is using characters. And this means that generating, of course, is fine. For code generation, basically, or template substitution, almost any representation is fine because you don't really care about the code. It's not really code. It's just you are producing whatever without reasoning about what you are producing. And characters is fine. The problem is if you need to do any analysis. In that case, you need to interpret the characters, and it means that you need basically to write a piece of the compiler directly in your metacode. So my meta function needs to parse the string. That's really far from trivial, especially if the language is complex. And another level is tokens. This is just a little bit more higher level. It's an higher level of representation compared to characters, but there's really not much of a difference because still you need to do sort of parsing, and if any analysis is required. For generation, of course, perfectly fine. And another form is AST. As you probably know, AST is an acronym and stands for Abstract Syntax Tree. And it's a tree representation of the semantic of the code, the meaning of the code. And this simplifies analysis, but the dark side of this is that the code represented as an AST can look weird. What do I mean with this? What you see on the screen now is the AST representation of the statement x equal x plus 1, where x is an integer parameter in C++. I used the clang to output the AST. There is an option for outputting the AST. And I represented this AST as a graph for easier reading. And as you see, we have a binary operator at top level. The root is a binary operator. The left side is a reference. The right side is another binary operator, that is the addition. And the left side of this addition is an implicit cast. And this is one of the problems that is often present in AST, is that the parsing can have weird transformation rules. On the source code, the left side x is absolutely identical to the right side x. But instead, at the semantic level, the right side is an implicit conversion from L value to R value. So when I think to code, I need to think this kind of stuff that can be different from the original code. And so when I'm producing, I need to produce this kind of node. And when analyzing, I need to consider that I might bump into this kind of node too, even if in the source this is not really present. And this is what I mean with alien. Metacode working on the AST can be hard to connect to what was the original code, especially for if the language has a lot of hidden transformation and semantics, like for example C++ in this case has, that is conversion from L value to R value. Okay, now we are going to see how metaprogramming is implemented in a few different languages. I've chosen 5 languages that are quite similar to C++ in my view. And the 6th one is completely different because it's dynamic typing language. And it's for the reason that, in my opinion, is still the gold standard for metaprogramming abilities. It has still abilities that are not even in the radar of the other languages. It's still ahead. And it's also a very old language. Not many have heard about Lisp, or maybe they heard about Lisp but just very marginal for a very short period, but they ignored completely. It's a language that was designed in 1958, and is still, in my opinion, is the best you can aim at if you are talking about metaprogramming, and we will see why. So let's start with C++, that of course I suppose everyone looking at this video knows about. It's a language that was created by George Strostrup as an evolution of the language C. Then we will go for the D language, that is also designed by a C++. Walter Bright was the one of the early implementer of an early one of the first C++ compilers, that was Digital Mars. I think now still the development has been abandoned. And while developing this language, Walter Bright decided that something they didn't like, in C++ approach, and so he went for its own language. And his view was also shared by another very famous person in the C++ world, that is Andrei Alexandrescu, that also helped shaping the D language quite a bit. Then we have C3. C3 is much less known. It's starting to get some traction now. It's a language designed by Christopher Lernow, and it's a lower level, I would say lower level than C++. Is another evolution from the C language in another direction. Basically, changing only what is considered to be wrong in C without adding much. Then we have Zig by Andre Kelly, that is quite popular now. It's still not 1.0, so it's still changing, but it's getting some traction. It's also a language that I would say a little lower level as an abstraction level from C++, what aims to be C++. Then we have Rust. Rust is very, very popular now, and it's also changing, so still not stable as a language. Apparently, in modern times, stable equals dead, so they don't want to be stable because then if something doesn't change, it doesn't break backward compatibility is considered to be dead, so uninteresting. And then, as I said before, we have a Lisp, that is a very, very old language, but is really powerful about metaprogramming. Okay, C++. Originally, there were only templates, so in the early version. Then we got constexpr, and one funny thing that happened is that a functional language was found to be present, and it was found by accident. It was present by accident. It was not designed to be there because of in the type system. This language was found because there are interaction of three different mechanisms. One was the overloading, the other was the recursion, and the third one is really weird, that is SFINAE. SFINAE is an acronym and means substitution failure is not an error. And it means that if you have an error, what would be a C++ error normally, but it's just one of a certain kind of error. So not all errors are the same. For example, missing a parenthesis is not acceptable as an error, but what was used a lot was a negative size array. You cannot declare an array with a negative size. This is an error, and it's normally an error, except when it happens in a very specific place of a template declaration. So not everywhere, must be in the declaration part of the template, the argument part of the template. And so if you have a certain kind of error in that declaration, then that's not really an error. Simply means that the C++ should ignore that template and not include it in the overload resolution set. So as you know, in C++, you can have a multiple function with the same name. This is called overload. And there are quite complex rules about which of the version should be chosen. And there are a precedence list, basically. And SFINAE basically say if you have an error when reading a template declaration, when considering a template declaration for the specific parameter substitution, if you get that kind of error, then simply ignore that template. So exclude it from the list and pick the next one in the priority. And so the trick that was used for quite a bit was declaring a negative array, and do this is as the default value for a template parameter that is not used by the template, was just there just to make SFINAE work. So if you make a compile time computation that returns a negative value, and this is very easy to do because you can have, if you have a say a Boolean comparison, this is also can be interpreted as a number 0 or 1. So you can say 1 minus 2 times the comparison. This is either 1 that is valid or minus 1. In that case, is an invalid array. And if you put this in the extra parameter of the template, you basically are able to include or exclude that template depending on this. And this is allowed for conditional. Then you have recursion. And so overload plus finite gives condition. We got recursion, so we can have loop, and we get Turing complete. And later, something more sensible was added, that was concept and if const expr. That is a better way to do conditional, basically. And C++26 will add introspection, and I think there is no code generation inside, as far as I can tell. I saw a presentation by Sutter on C++ 2025 conference, but I tried a few examples, it didn't work. So maybe I did something wrong. And I think that this is still not inside. Maybe there will be something on 29, C++ 29. And consteps all the things is something I took from a presentation by Jason Turner that say we need more consteps. We want consteps to be very useful for everything. And I don't agree. I don't agree at all. I don't want consteps actually. And with this I mean I don't want a keyword consteps. Why I need to say that this should be computed compile time? Could be computed compile time. If could be computed compile time, then I should be able to call the function without the need to mark that function as consteps. So I don't think consteps are the things, so we shouldn't have consteps, we should just use C++. That's my view. And and that's it. So this is an example of C++ template. It's a very stupid example, sorry for that. But it basically is using if const exp. That is basically the compile time if done in a saner ways compared to SFINAE. And we are checking if something is integral. This is also something that's simplified a bit over the years. Long ago, what that means is integral dot value, something like that. And we are returning a string, and that depends concatenating the type with the value. And something that is important to understand is that if const exp, the branches that are not taken by the if const exp are not even compiled. They are checking for the basic tokenization rules, but they don't need to be able to compile. And this was the and the same as SFINAE. In case the header was giving this kind of error, this specific kind of error, the rest could contain also other errors. Of course, not errors about, like I said, missing parentheses, but certain kind of errors were allowed in the other part of the template. Okay, the language is very similar to C++. Like I said, Walter Bright was the author of one of the early C++ compilers, and but it's a better implementation, in my opinion, for the template. So still the template approach, it was the main original tool for template. For quasi-quoting, it uses template, but it's a better implementation. There are a few details about this. One important one is template mixin, in my opinion. One of the this is spoiler alert. One of the problems with C++ with template with quasi-quoting is that the granularity of the template is too huge. A template must be the full function or the full class. It cannot have a template for some just a simple smaller part. I cannot compose different templates, and this is very useful normally. And this is just not something that is allowed in C++, but is allowed in D. So this template mixin allows to take just a little function, a little declaration, a little statement, single statement, and to compose this. This statement must not be able to be compiled alone. So it's considered only for compilation when included in a context. So this is a very different approach. And it doesn't have const exp, with the meaning that any function is const exp. So you can call any function. If the functions, there are limits on what you can do at compile time. But if, for example, a function is pure, it's just manipulating input and output with no dependency on with stuff, you can just call it a compile time. So there is no const exp keyword. And this is direction, in my opinion, is more sensible. And the name they use is compile time function CTFE. And also it has the string mixins. String mixins, it means that you can have D function. Like I said, it doesn't need to be construct these functions. There are any D function that there are some limitations, but basically you can use all the data structure, all the code you want in a D function that returns a string. You can put this an invocation for this function at compile time in many places, not in every place, but in many places. So where you have a type, where you have a statement, where you have a declaration at top level, you can use those string mixin. And basically what the compiler does is call this function at compile time, and the output is like replaces what was the invocation of this function. And so you can generate code that will be read by the compiler like if it was present instead of the invocation. And also what you generate cannot be really arbitrary. You cannot just generate a single open brace, for example. So must be as some limitation of what it can do. But it's very, very general. and so you can inject the source code. You can generate arbitrary code. And for introspection, it uses a special API. So when you pass parameter to a CTFE function at compile time, these parameters can be also structures data, and this can be introspected using traits. This works at compile time only. If you want this at runtime, you need to generate data structure that you will access at runtime. And as a meme, I will put it's just the code. It's not const express, not const val, it's not recursion with finite or weird stuff. It's just a regular decode. And this is an example of the very trivial example. This make getter is a string function, it's a regular D function. This can be called at compile time, runtime. There is no context needed to be declared. It takes a string as a name, a string parameter name, and returns int space concatenated. The tilde is concatenation, string concatenation with the name, with the parentheses, and returns underscore the name. Semicolon, close brace. And I can use it, for example, in a structure declaration. I can say mixin make a getter x, and this will create a getter for the underscore x. And sorry again, this is a very, very tiny example, doesn't really make much sense. I mean, the code that you save in this case is, even if you save very little, it really doesn't add much in this case, but just think to what you can do in general. You can produce whatever you want in using the full power of the D language. Okay, C3. Like I said, is very not as popular as D. Is also kind of niche language, but it has a very, very strong supporters. They are few, but they are very convinced that it's a very good language. I don't have much experience with D, but they looks interesting. C3 is almost the same, but they are even fewer, but is getting some traction. And C3 uses still a template-like approach, but is let me say a bad word. That's PHP. Is more or less like web page creation with the PHP language. So where you have your C3 code that is very similar to C, different syntax. In the idea of the author is a better syntax, more logical syntax, more regular, and then you have those macros that is, they have a separate language for expansion. So they are template, but you have loops and conditional that are marked clearly using dollar signs and other hash marks and stuff. So you can see where the substitution is done and when the computation is done at compile time. And uses compile time variable expression and macro based code generation. So there is no arbitrary code generation except for a single case that is at top level. There is the possibility to actually call an external program and include the result. So basically it's like include but with invocation of an external program. And like I said, it uses special macro syntax. So it's basically more or less like C, but instead of the preprocessor, it uses a Saner language. Preprocessor is very, very weird if you ever try to do anything with it. And very little power in the preprocessor, except a few ad hoc extensions that have been added. But instead, C3 has a real language that is for compile time macro expansion. And also there is, like I said, arbitrary code generation ability, but only at top level. So that's why I put the word limited. This is by design. I have to say I don't really understand what is the reason why I can't just call for the same in the middle of my in a local scope. I mean, why the compiler cares? And this is one of the cases in which the language designer thinks that you shouldn't give this power to the users because they would abuse that power for do bad stuff. I don't like this view at all. I am more for freedom and education to avoid bad uses. But this is what the C3 language does. So I use this meme to say that, okay, no preprocessor, let's use macros. This is a very simple example. It's not a very smart one. Once again, sorry, but I need to just use one slide. And here we see a macro. That is the definition instead of define. The keyword is macro. Void, logif, enable. So basically, this is uses the @sign for the macros, both a declaration and invocation. So you cannot confuse a macro invocation with a function invocation. So this is clearly marked. Differently from, for example, the C preprocessor. This is one of the mistakes of the C preprocessor, in the opinion of the author. And here, $if is a conditional compile time. So it's marked with a dollar. And this is a parameter. This $enable means that it must be a compile time constant, a compile time known value. In this case, is a true value. And this part is what is expanded. So basically, we are seeing a template, but this included only if enable true. Otherwise, it's just empty. So this function is going to have an empty body. And that's it. There are a few, I think, I hope we're not making confusion with another of the languages, but the braces, you see them, they are present, but they are not really there in the expansion. So they will be just a single line in case of expansion without the brace. I hope I got this right. I'm not making confusion with another language. Sorry if this is the case. Okay, Zig. Zig is very popular, and it has this concept of comp time. And this comp time word means that compile time execution. Templates are very simple. You look at them, they look like normal C declaration or C functions. For the function, they look like normal C function, except that some parameters are marked as comp time, and those are basically templates that can be expanded if needed by when called with types parameters. The language is identical to Zig. The semantics is very close to Zig, so it's almost Zig for the language. There are a few differences, but this comp time allows for very arbitrary computation at compile time in Zig. And introspection, like in C3, like in D, is done using a special API. If I'm not mistaken, it's still something that is stabilizing, so they're changing a little bit the API, so you can introspect the code. And for now, if I understood correctly, it's just for structures. So you can introspect a type, but you cannot introspect a function. So it's not looking inside the really code, only inside the structure declaration for introspection. And generation is also only about structure. You can generate types at compile time, new types, arbitrary compile times. So you can generate arbitrary, so not only template based. You can build a type from scratch at compile time, but you cannot build code from scratch. And if I understood correctly, this is not an oversight or a mistake or a bug. It's a design choice. I'm not sure. Maybe it will change because, like I said, the Zig is still in flux state. And like I said, there is no ability to create code from scratch, only data structure. And so it compiles regular code, always a spin. This is an example, quite a bit more convoluted than other example, more sophisticated. And this maybe makes even sense as a real example. I'm creating a zig function that, as you see, accepts a comp time type parameter. So this is meant to be called at comp time. Actually, two compile time parameters. One is the type, one is the dimension of the vector, and this creates a type. As you see on the upper right here, this the result, the return value type of this function is a type. And as you see, we have return struct. So we are returning a type. And this type uses template substitution, basically. So we have the T, the N, and at sign this is a trick to be able to refer to a type inside the type, even when the type has not yet a name. So this has no name, so you can, with this, you get a reference to the same type. And this is a loop that implements addition, element by element addition. This is a standard way to make loop in Zig, so it's not special syntax. And here is an invocation. As you see, here we are not marking this as in any special way. So, for example, the choice of Zig was to keep the usage of this kind of macros, basically compilation time functions, marked the same as a regular code. And then we get the Rust in our list. It's the last of the C++-like languages, so strong typed and a lot of other characteristics similar to C++. Rust has basically two different engines. One is declarative macros. That is macro rules is the syntax for this. And they are basically templates with the addition of a pattern matching at the beginning. So instead of having a template to have in C++, you will do several templates using overload. In Rust, they use instead these macro rules with dispatching using pattern matching. And there is a DSL, like in C3, you have a different language for expressing the expansion, controlling the expansion with algorithms using conditional and loops, stuff like that. And then it has a separate tool that is a const function for compile time computation. So if you need to make a computation instead of a template instantiation, you have a const function that is like a constexp, more or less like constexp. I think it's very, very limited in what it can do, more than constexp actually. If I'm not mistaken, Rust is also changing all the time, so maybe it's something that was removed in a later time, in a later evolution of the language, in respect to when I read the documentation. Oh, okay, maybe I forgot this very important point. I don't have any real-world experience with those languages. I just read the documentation, maybe played a bit in the playground or installed the compiler and just tried a few examples, but I don't have any real experience in those languages, so you should take what I say with a grain of salt, because maybe I'm saying something wrong. If I do, please let me know, because this is something I really care about. If I said anything wrong, anything factually wrong. And this is also a declarative macro const function with compile time computation that are very limited, and procedural macros. This is a completely different beast, and it's the of all the languages we have seen so far, it's the only language, Rust, in which metaprogramming is done using the real Rust language. Because the procedural macros are real Rust code, normal Rust code, no limitation at all. The only thing that you have to say is you have to inform the compiler that a certain crate contains procedural macros. My guess is that this is needed because those crates need to be compiled first, because you can then use those crates directly at compile time. So just knowing the interface is not enough. The compiler has to invoke your Rust code at compile time, and so that crate must be compiled first. So declaring which crate contain procedural macros is important. And also the dependency of the interfaces forces the order of compilation of those procedural macro. If a crate with the procedural macro uses another crate with procedural macro, there is a topological dependency. I think that, I don't know how, but I suppose that probably loops are not permitted in this case, so dependency loop are not allowed. But for example, I don't know if dependency loop are allowed or not in regular crate. There is no any technical limitation for this, for blocking this, but mutual recursion, there is no problem if you just need to know the declaration. But for macros, of course, you need, because those macros are actually invoked at compile time. And the procedural macro just takes a stream of token as input and returns a stream of token as output. So it uses tokens, so not characters, but is absolutely general. In addition to this, there is a predefined crate, a standard crate that is part of the library, that is named the SYN, SYN, and that is able to pass a stream of token into an AST representation. So your procedural macro can use the AST representation, and it's also able to take the AST representation back to a stream of token for generation. Something weird, in my opinion, is that this SYN crate is not internally used by the compiler. So it's a different, distinct implementation. And I don't know the technical reason for this. In my opinion, that's kind of weird. Another thing that is weird is that Rust has many different macros in the language, are part of the language. For example, you have for formatting, you have different macros that are available when you use Rust, but they are not implemented using the Rust system for macros. So there are many built-in macros that are not built in Rust. They are not procedural macros. I don't know also if this because it's technically impossible to do, or just difficult, or just not convenient. But that's something that is kind of weird to my eyes. One thing that also is done by Rust, and as far as so Rust only, for the language we already saw, is that there is the agene is implemented automatically. What is agene? Agene is when you have a metacode that injects code. This code can inject variables, names, and you must be careful of not stepping over variable or names or type names or function names of the user. So if you define your local function, but then you expand part of the user code, but this code uses a function with the same name but was a different one, was a function from the user, you bump into a problem because you are either the user code calls your function, or your code is calling the user function instead of your own. And this problem is called the hygiene problem, and is something that Rust macros are handled automatically. And this is the slide. So we have a constant function that's very limited. It can do some computation. Then you have macro rules, that is the template expansion with a separate language, DSL for expansion. And then you have proc macro, that is the most powerful tool. And this is a very simple example of macro rules. So we have a create function macro that takes as only parameter an identifier. This is the pattern matching happening. So if the argument to create function is an identifier, then this expansion is taken care of. If none of the expansion takes care, you get a compile error. So at least one must match. And you can have a recursion here. So you can expand to use create function again. Not the case in this case, but it's something that is possible. And here you see the expansion that uses fname to refer to the external parameter, and it's just expanding to another macro that is a predefined macro that is print, and basically logs out this print call. As you see, we have a stringify that is another macro that, given the identifier, returns you a string literal identifier. This is a predefined macro, and so what you get is a println that is calling with a format string and a string literal. Okay, there is a mistake here, because when you invoke a macro, you must use an exclamative mark. So it's Rust makes a clear distinction between function invocation and macro invocation. Also, so this is my typo here, and you get this stringification. But basically, we'll expand in a println with a format and a string. And as far as Gemini told me, this won't be expanded in a single literal. So the println macro is not smart enough to include directly literals passed as a substitution point in the template of the format string. But we can do that explicitly if instead of using this expansion that is expanding to a regular println, we do a different expansion. So we call concatenation, that is another compile time macro that is available in Rust, predefined macro that can concatenate strings, and we get the same. And okay, this is the Rust example. Now we have Lisp. For Lisp, Lisp is a very different language from all the others we saw. It's by default dynamically typed language. You can declare types, but by default is like Python, to say something very similar. And one big difference is that the source code in Lisp is not a stream of characters, but it's already a data structure. So Lisp code is data by definition. It's not something that you can represent code as data as code. It's actually data. So the input to the compiler is a data structure. It's not a string of characters. There is a separate part before that translates characters into the data structure, but this can be used also for regular data, not for code. Metacode is a regular Lisp code. Like in Rust, there is not a subset, not a different language. You can do whatever you want, and there is quasi-potting, but just an helper. It's just a syntax simplifier. And one difference between Rust and Lisp is that in Lisp, quite a bit in all the system I look at, and also in the ones I implement myself, most of Lisp is written in Lisp itself. So you have a very basic Lisp system. Everything else is built in Lisp using Lisp macros. It's not predefined the compiler. So the compiler doesn't need any special case. So it's very, very simple. This is something that is a few slides now. Now I will explain more detail. And metacode normally works by lowering. So you basically create a macro that introduces a higher level concept, and this macro basically translates this higher level concept in the concept without that macro. So what would be the same expressed in a Lisp but that didn't have that macro. So this is what is lowering. And so there are not many macros that are predefined that do magic. There is no magic in Lisp. Basically, we have a very basic, very basic kernel, very limited, minimal kernel, and then everything else is obtained by lowering. This is very common in Lisp. And I put this slide. I've put this slide because it's really it's not something that can be said in 10 minutes, but if you really take some time looking at the Lisp ability in metaprogramming, I'm talking about the ability of metaprogramming, it's really on another class. It's something completely different. Okay, now I have this table that represents all the languages I've talked about in this presentation. So we have a C++ that has quasi-quoting, but not a really nice form of quasi-quoting. There are a few slides now. And computation that is not really nice as computation. Like I said, you have to mark what is used. You have many limitations. They are being removed as time passes, but I still remember, like it was yesterday, but it was probably 15 years ago or something, at a Lisp conference, was a C++ 11, was the new thing at the time. And they had constexp. The very early version of constexp was very, very limited. And I remember saying at someone at that conference that I wanted a constexp open. And I can still remember the bug eyes they gave me. Like they were close to call the police for get me escorted out of the conference for saying such a, this is such a bad thing. I mean, I wanted to open. I'm crazy or whatever. Just take me out. And it's funny to say that now every 3 years they add something, and probably in another 30 years we will get constexp open because there is no reason for not having it. And constexp open. And but right now it's still limited. There are a few limitations about what you can do in a constexp function for no real reasons, in my opinion. There's no code generation, no code analysis, and no code transformation. Code analysis will be in 26, apparently, for structure only, like all the other language we are going to see, with the exception of Rust, that also can introspect functions. And code transformation, of course, not. And then we have the language that has much better quasi-quoting, in my opinion, much better computation abilities. Code generation is full power because you have string mixin, so you can generate anything you want to generate. And code analysis using APIs. And code transformation is not present because introspection is only allowed for only for structure. So the code transformation, I mean function code transformation. This is not of function code analysis. And then we have C3, that is nice quasi-quoting, little better quasi-quoting. Computation is nicer. Code generation is so-so, in my opinion. And code analysis is also, this is my impression. I don't have much experience, so maybe please don't take this as too much of opinion. It's an opinion, but it's not based on long experience. So just the first impression. Okay. And then we have Zik that has a quasi-quoting that's okay. Computation is good because we have contain you can do. Code generation is not allowed by design, so this is a choice. And code analysis is better API than C3, in my opinion, comparable to D. And code transformation not because you cannot generate code, so you cannot transform code. You can generate generate structures. That's okay. And then you have Rust. Rust is good quasi-quoting with pattern matching. I would say, I don't know, const function are limited, but it's kind of okay for computation. You have code generation, full capability with proc macros. You have decent code analysis, and actually you can also introspect function because you have procedural macros can read anything and using the sync rate can use AST, and so you have full metaprogramming power with some limitation. That might be compiled first. You don't have scoping and things like that. A code transformation is possible. And then you have Lisp, that is really another thing. Now I have a few slides on Lisp. I put them here because Lisp is, like I said, very different from all the other languages. So if you know C++, that is my supposition, if you're watching this video, then reading the other languages would be pretty natural. I mean, they will look not too weird, they're very similar. Lisp instead is very different. So first thing is homogeneity. That means that the, like I said, the Lisp source code is a Lisp data structure. And coded data is code is literal. I mean, this is the thing. It's not a view. Is not. It's just what it is. And metacode is just regular code. So you have just this function, and there is no runtime compile time distinction. Almost. The example I will use are from Common Lisp. Common Lisp has some limitation for reasons that are complex to explain now. But basically, you know if it's compile time or runtime. There is this distinction is in some form present, but is really tiny compared to other languages. And this is not something that must be present in a Lisp system. I implemented the Lisp system in which compile time is just not a word. I mean, there is no compile time. There's just runtime. And because compilation is a runtime function call. I call the compiler passing a data structure for the input, and I get executable code back. So it's just a library function. The compiler is just a library function. This is possible to do. It's not what the common Lisp system does for compilation, but it's not something that is impossible to achieve in Lisp. And this is an example of the syntax. I understand that can look weird compared to other languages, but it's very simple. So we have list is elements separated by spaces and enclosed in open parentheses. In parentheses. So there is no comma for separating elements, so we don't have the trailing comma problem of JSON, something like stupid like that. And we have one concept that is present in Lisp is that the elements can be strings, they can be numbers, but they can also be symbols. Symbol is a name. It's like a string, but it's not the characters, just an identifier or a keyword or a name. Okay. So here we have a list. This is a list that starts with the symbol define, that stands for define function. Then we have the function name, that is another symbol, that is Fibo for Fibonacci function. And then we have a list that is the list of the parameters. Here we have just one parameter that is n. That is a number. Like I said, the Lisp is, you can think to it like Python, so dynamic typing. So we know that's a number, but it's not stated here. You can state this. You can say in Common Lisp, okay, I know this is a number, must be a number. So you get both compile time errors and you can get compile time warnings, actually. And you can get either runtime errors or optimization for speed if you assume we not check if you want to go fast. And then we have a conditional that is a list starting with a if. And here we have a function call. A Lisp has no operators, no precedence, no associativity, because there are no operations, just function. So this is a function named less than. That's a valid name for a function. So we are comparing n with 2. The other parts are the arguments. So I compare n with 2. This is the case when it's true. The value must be 1. And this is the case when it's false. That's another function call. The function is named plus. And the elements are other function calls. I'm calling Fibo, that as you see is the same name of the function I'm defining. So this is a recursive function. This is the naive implementation of Fibonacci function in Lisp. I want to conditional. Conditional is an if, it's a list with 3 or 4 elements. The first one is if, it's a keyword, as I say. Then we have the test, that will be an expression, can be a variable name, but can also be another list with more complex stuff. another expression that is the value if true, and optionally if the value is false. This is not a function call. This is basically the AST node for a conditional. That can have three. It's an AST where we have either 3 or 4 elements. Actually, 2 or 3 child, let's say, elements in the AST node, and it works like in other languages. Okay, one pattern that is very common in Lisp, but also in other languages, is when you have a conditional and without the else part, only the true part is present, so the false part is nothing. But that part is composed by several steps. Oh, by the way, Lisp is not a functional language. You can find this on the internet, but it's just a false thing. I mean, if Lisp is functional, then also Python is functional, because it's very, very, very similar to Python by default. It's very, very similar to Python, if we exclude the metaprogramming abilities. And so it's not functional. So statement can have everything is an expression, different from Python, but you can have side effects, and so it's not functional in any. It's not purely functional at all. So you can have multiple. Makes sense to have multiple expressions one after another, and the value is the value of the last one. This is what program is. And more or less like open brace in C, is a block in the C or C++ programming language. And so you have a test, and you only have a body composed of several elements. This is a very common use. It's so common that Lisp provides a dedicated syntax form for this that is named when. The when conditional takes a test, and then just all the other elements are the body. So you get one level less, so you don't need to open a brace, basically. And one important thing is that if when was not present in Common Lisp, it's already present in Common Lisp, but if was not there, it would be very easy to add. Because this macro definition is what is implementing when in Common Lisp, in a Lisp that does not have this function. This syntax construct. And how it works, basically instead of saying defun, I say def macro. Def macro means it's just a regular function, but the compiler is informed that this function should be called at compile time. In Lisp, the macro invocation is not marked in the syntax, so when you see a list where the first element is a symbol, that may be a macro invocation or a function invocation. You don't know looking at the calling side. So you decide if it's a macro or not at the definition side. So I define when to be a macro, and the only difference that this is a regular Lisp code with all the abilities of regular Lisp code, but will be invoked when the macro, when some code is using the macro at compile time, not at runtime. And it's named when, so this is the name of the this macro. We receive a test. This won't be the value of the expression, but will be the expression itself. So basically a macro receives the source code of the parameters, not the actual value of the parameters. That will be known only at runtime. But the source code is known at compile time, and this is what is passed to when. That is a macro. And rest means it's a variadic function with all the other arguments are collected in a single parameter named body. And this body is a list of expressions. So, and this is the implementation. It's an invocation of the list function. It's a regular function named the list that creates a list of the elements, like in Python. And the first is quote if. That means it's not a variable. I need the word if as is. This is quoting. The single quote before is just means the next expression as is without evaluation. So the value will be if, the symbol if. Then we need the test, that this is the argument we got passed. And the third element will be a concatenation of a list containing the keyword progn and all the body. So will be a list that starts with progn, and then we'll have all the other expression. And basically what it does, this function, is translates when test into if test progn expression. Because the compiler see when calls the macro, this macro we saw before, passing test expression and this in the list body. And then the expansion will be a list starting with the if, the test, a list starting with progn, and all the other elements concatenated to the same list. So this is the expansion. Macro expansion is the technical term that's used in the Lisp jargon. And well, something important to understand is that this is just regular Lisp code. It's not a template. It's just code. And if written in Python, this will be more or less like the same code. If the implementation was in Python, but was in Lisp code, sorry for this weird, but this is probably easy to understand for who knows Python. So basically it's a function that takes test and arbitrary number of elements after, and then returns a list that starts with a keyword, the test, and the concatenation of a list with just a keyword with all the elements. So this is the Python implementation of the div macro, so to say. One important thing is that so this doesn't have quasi-quoting, doesn't have template, it has templates, and this code is actually equivalent to this code. It's just much shorter. But this is not a special case. This is something I can use in any Lisp program, not only in macros, can I use it for, and it's just a list creation utility. So the back quote means this is a quasi-quoting, that's the name. And means that whatever is just a template, and the comma is where the substitution is going to happen. It's more or less like the back quote in JavaScript, when you put in strings, you know, and the comma is equivalent to the $open brace in JavaScript, JavaScript template. And so we have this comma that means, okay, this is, you need to take, the next is an expression, is not literal. And this is a different expression, this is a different way to refer to an expansion that is called splicing. The expression must be a list, and instead of replacing the list itself, we'll put the element of the list. So basically, this allows me to do the concatenation in the template without having to write it explicitly. An important point, both test and body, when I use comma or comma splice, here I'm using just a parameter name, but I can use whatever I want. So including an expression. I can use a comma, open parenthesis, then will be a Lisp expression doing computation. So this is just expression. Like in JavaScript, it's an expression, not like in C++, where must be a template parameter, because it's not marked. It's just the name of the template parameter is substituted. Only the substitution works for parameters. And okay, back to the C++ metaprogramming, and here I'm gonna say why I put some tiers on the table, and why I think that C++ metaprogramming has problem. There is something wrong with C++ metaprogramming. Basically, C++ metaprogramming, what provides for, what are the metaprogramming abilities of C++? They are template substitution, that is named the quasi-quoting, that is the most trivial example of metaprogramming, badly implemented. And that's it. That's what C++ provides for template metaprogramming. For metaprogramming, only template substitution and bad implementation of it. And almost, because now they are adding something, so we got constexpr, that is okay, better than using template expansion to do computation. And they are now, we will get we don't have yet, but we will get, for example, introspection, some limited form of introspection, not cogeneration, nothing fancy, but something will be. And just to give you an idea how bad the situation is, we only got strings. I'm not talking about the weird stuff. I mean, just being able to use the strings at compile time just a few years ago. It's not something that it took many years for C++ to get strings. That is how bad it is. And template substitution, I mean, badly implemented. Why? First of all, the substitution points are not clearly marked. So when I say the symbol X in a template, is this literal or is this substituted? Who knows? Go check the template parameter list. Also with some weird rules. For example, you normally can open brace and declare a variable named X in C++. But this maybe is not valid in a template, because if X is a parameter, you are forbidden from shadowing. No idea why, but this is what the rules are. Maybe there are technical reasons, but I don't know, it's kind of weird. And all this could have been disappeared by just using a single character to mark the substitution point. Would be easier for the readers, easier for when you write the code. But no, it's just using, it's not clearly marked for reasons that I don't understand. Another big issue is that this is a bigger issue, is the template must be the full function or the full structure. There is no partial template possible. This is very annoying. You are forced to use utility classes just to get something, to have a template for you reuse a template inside another template. You have to make a different class, because the template must be the whole thing. They are not the template mixin, for example, of D, that allow for single chunks to be used as template. And the substitute value can be an expression, but only a parameter. And this means that if you want to do any computation, you must use an utility class to do the computation. This was very common long ago. Now with constexpr you can do some computation at compile time, but still you need to do a separate constexpr function to do the computation, because when you use, let's say you have two template parameters A and B, and in your template body you write A plus B, that computation is not done during template expansion. What happens that A and B will be substituted, then the compiler will normally use constant expression for the constant folding for the computation, but it's not done during the expansion. So you cannot use an expression, let's say a conditional or whatever. You must declare a separate template just to do the conditional. I cannot say here I want this or this stuff or this other stuff. You must use a different template just for doing that. And C++ compile time computation is something that happened by accident originally. So it was discovered that it was possible to do the computation because of three element X. Like I said, there's overloading, finite, and recursion. And all three actually gives you this triplet gives you Turing complete language. And what is Turing completeness? It means that you can compute anything that can be computed. So really you can do any computation. But being Turing complete means that any computation can be implemented using C++ template. But it doesn't mean that if you have a Turing complete language that you should do the computation using Turing complete language. For example, there are many languages that are Turing complete, but they are absolutely highly used as a programming language. Even a game of life, with the cells, that the evolution thing, that's Turing complete. You can build a computer using game of life. You can look on YouTube for videos where game of life is implemented in game of life. And another example I often do is the language brainfuck. This is not a bad word, it's the name of the language. And it's Turing complete. It's only defined by 8 characters. For example, even the number 14 is difficult to implement. A program that returns 14 in brainfuck is not trivial because you don't have numerical literals. You have to start from 1 and increment until 14 to get the number 14. But it's still incomplete. You can find translators from C to brainfuck. And but doesn't mean that we should code in brainfuck. It's still incomplete. Can implement anything. So we should code in brainfuck. In my opinion, the answer is of course no. If you want to play, that's fine. That can be even interesting as an exercise, like walking on your hands. That's nice. But do you want brainfuck code in production? You want to maintain brainfuck code? Of course not. It's hideous. It's nonsense. And so C++ was discovered to have this kind of Turing complete sort of language that you had to use finite and recursion just to do iteration or conditionals. And but this I think that this discovery damaged C++ seriously, because having a way to do trivial things prevents C++ from getting a real metaprogramming solution for anything that is not trivial for more than 20 years. And so having this ability was what, in my opinion, slowed down decent C++ progress for the metaprogramming side. And even if this waste was terrible, and so this terrible was really barely usable. In the origin, the compilers were getting internal errors or exploding all the time when you were using this kind of metaprogramming abilities. Why? Because the designer of the compiler thought that you just wanted to do template substitution, not computation using recursion. So they were, after 3 levels of recursion, the compiler would explode. And today it still is absolutely complex to write the templates. It's even the users of the template for the writing. It's even the compilers, where you have template code that takes forever to compile. And it's still today it's impossible to debug. So I want a template code compile time computation is just computation. I want to do this debug, for example. I want to add my prints. I want the step into the debug. And this is still, there is maybe excluding one case, still something possible. You just run the code, whatever. The error message when you make a mistake in a template expansion are literally a joke. I remember when I started working for the current company, there was a colleague that was using a plugin from a company. The only reason for the plugin to exist, the only capability of the plugin was debugging template errors for Visual C++. And that plugin was the only, if I remember correctly, was the only tool sold by the company. So the idea that you can have a company, business, that is only deciphering error messages, in my opinion, is telling you a lot about how bad those error messages are. And this is still today they are the same. Now, concept in theory, they should simplify. My experience is for now, I still get 20 screen of error messages because I forgot a const. And we're really garbage. It's very difficult to find where is my mistake when using this stuff. And this stuff is so bad that it's really like a joke. I mean, it's different to make to exaggerate how bad it is. It's so bad that it's not possible to exaggerate. And it's still today. So this is very, very horrible. But you can do stuff with this stuff, and this prevents from getting a nicer way, in my opinion. And there are a few big issues with metacode. For example, metacode is complex by itself. There is an essential complexity in metacode because the code, what metacode manipulates, is complex. It's not an array of numbers. It's something that is recursive in nature. It's as a reference, it's really complicated stuff. So the metacode, code that manipulates this stuff, cannot be trivial. but much of the complexity comes from in C++ comes from how bad the syntax it is and the semantic it is. The most complex code is, the most complex metacode manipulated is in even worse form. So if code is complex n, the metacode for manipulating that code is complex n squared, because the way it was metaprogramming, because you are manipulating something that is really complex. And C++ complexity, the syntax and semantic of C++ is really complex. And another thing, that static typing, that is a fundamental idea in C++, doesn't really work well with metacode. This is something that has been also, apparently, this is my personal opinion, I wrote a lot of compilers and stuff on metacode, and this is something that I got from, I found myself, but apparently the people in the committee agree, because C++26 will have introspection, but the key element of this introspection, that is this info object, so to speak, is actually dynamically typed. So there's just one type for all the stuff you can represent. And this works much better than static typing. C++ is about static typing, but metacode doesn't work well with static typing. It's easy to write, much easier to write dynamic typed metacode. And also in C++ there's this compile time, runtime, split up sessions. And I don't know why there is this idea. In my opinion, if it's user code executed, that's runtime. If it happens during compilation, who cares? It's runtime. It's code, user code executing. And but in C++ instead there is this. There must be a clear distinction. I don't understand why this is so obsessive about separating compile time from runtime. And also metacode is about function bodies. This is something that is not even in the radar. I didn't see anything even talking about this. This seems an idea that is really far, if ever, will get to C++. And why I think there is no hope? That's the current situation, but why I think there is no hope for C++? Every 3 years, the artificial complexity of the language increases. So we get more syntax, more semantic. And every increase will make metaprogramming harder, because the language becomes more complex, especially because it's not a complexity that is automatically reduced. There is no lowering idea. There is more built-in complexity that is not expressed in a previous existing concept. And the syntax gets more complex, of course. Semantic and syntax get more complex. Also, we get more ad hoc solution, built-in solution. For example, in my opinion, we get contracts, for example, that I think they were completely unneeded. I mean, I can implement contracts. Right now, it's very easy to implement a contract using some bad tricks. If you want to release some contract macros, some abilities that is implemented in what is already C++, we want to define a standard library for contracts, that's fine, in my opinion, but another ad hoc syntax, another syntax twist just to add contracts, in my opinion, is totally unneeded. It's actually damaging C++. And this is not a juvenile error, it's something that is happening today. They added contract yesterday. And so this is I don't see this is gonna slow down. The addition of bad stuff like contracts is not bad in absolute. It's better that they added to the language. Why do you need to add this to the language? Add it to the library. Make a library for contracts if you really think that this is the best thing in the universe. And the compile time and runtime split is still considered absolutely important to understand. Important. We need to mark compile time and runtime. This is totally nonsense. And all this, okay, there is still no code representation inside. This is what makes me think that the programming, C++ metaprogramming is fucked up beyond any repair. So there is no way this is going to be fixed. But I need to add one thing. Please remember that I'm old. So maybe this is just my part that is yelling at the new stuff and saying this is bad because it's new. And that's it. So the presentation is over, and please remember that, like I said, I experiment a bit with a lot of languages. I studied a bit of language, implemented many of them. But in this example, I'm talking about 6 languages. And most of the presentation is from reading the documentation. So if I made any mistake, please let me know. And don't take my word for granted. Read about other languages. Something that kind of confuses me is that there are people that say, oh, metaprogramming is absolutely great in C++. You can do amazing thing, but they didn't see any other language. It's like saying, oh, this restaurant is absolutely fabulous. Did you try any other one? No. How you can say that's fabulous? And so please go around and check other languages. The documentation, maybe write a little project in them just to get a taste of what others can do before saying that C++ is amazing. And please also be careful about template metaprogramming in C++. That can be a challenge. And if you are smart, your brain likes challenges. But please remember if the challenge is real or not. For example, in the early C++ day, even making a loop was not trivial. And people was getting this dopamine shot from, oh, I was able to implement this stuff that, use the recursion to make a loop. But please remember that this limitation, that C++ template metaprogramming cannot do loops, could do loops. Now you have context loop, but in the beginning it was just you had to go recursion and finite and bad stuff. This limitation is not real. It's just because C++ decided that you don't have to make loops. You have to use recursion. So when you overcome this limitation, you didn't accomplish anything. You just get over an obstacle that was invented. It was not something real. You are not solving a real problem. You are just solving a puzzle, a pointless puzzle. You are coding hello world in brainfuck. After you do this, you didn't accomplish anything real. You just got over a stupid limitation that is part of the problem. You solved the puzzle. And but this can be problematic because if you're smart, you can be sucked into writing template metacode. Why I'm saying this? Because I've been there. I wrote metacode that now I have regrets about because that's in production and it's a bad idea. And maybe my metacode was not really super useful, but when you write it, you get the impression that you did something. That impression is false. You just got over arbitrary limitation. You didn't solve the real problems, but you got the dopamine shot. It's basically nerd sniping, if you know what I mean. Okay, that's really all. Thank you for watching, and see you next time. This is sorry. Oops. Oh, sorry. Okay. Okay. Okay.